Hello everyone, here's another Physics 30 example. This is lesson 7, the last lesson from unit 4 on electromagnetic radiation, and this one is on diffraction. So here we have a diffraction grating question. We're given the wavelength of the light being shone through the diffraction grating, and then we're given the number of slits per millimetre of the diffraction grating. We're told that on a screen, a certain distance away from the diffraction grating, we're seeing the first maxima appearing at 26 centimetres, and we need to determine the distance to the screen. So here's just a top-down view. This would be the diffraction grating here, and you can see I've drawn these tiny little slits in there. So representing double slits, but actually what we actually have is hundreds of these slits. Thousands of them on a typical diffraction grating. In fact, 700 per millimetre. We'll deal with that in a minute. Then we have a distance. I've done a dotted line, a distance to a screen, and on the screen, because we're shining a light through a diffraction grating, on the screen we're going to get some an interference pattern occurring. So we're going to have a central. We're going to have a central dot in the middle, the central maxima, and then we're going to have smaller dots. So we're going to have a bright dot in the middle, then we're going to have no light where there's some deconstructive interference, and then we're going to have constructive interference again at a certain point away, and then further away we're going to have more constructive interference as we go up. So this is going to happen on both sides, but we're only going to be interested in one of them. So let's just go ahead and draw some triangles from the center of my diffraction grating to my first bright dot after the central maxima. This is the one I'm interested in. So what am I trying to do? Well, let's go ahead and put some values in. The light is being shone from this side of the diffraction grating, so let's put our wavelength of light here. So I've got the wavelength given, that is 550 nanometers. I'm just so I don't forget, I'm going to put that in scientific notation, 10 to the 9, there it is. Now let's deal with the 700 slits per millimeter. If we're going to be solving this question, we're going to be using our formulas from our data sheet, which is either d sine theta over the n number, in other words, how far it is away from the central maxima, or the dx over nl, which is our small angle approximation. So we'll address that in just a second, but let's look at the d value. This d value appears in both of these equations. The d value is the distance between the slits. And so in this question, we're told 700 slits per millimeter. This is done notoriously badly. A lot of people will just put this 700 in thinking that's the number for D, but it's not. What we have to realize is that if we have 700 slits per millimeter, let's write this out. We'll use unit cancellation to do this. 700, let's go slits per, well, when we say millimeter, we're really meaning 1 millimeter, aren't we? So there's 700 slits per every 1 millimeter. So let's cancel this out with some unit cancellation. In other words, we're just going to multiply by some ratios which we know to be kind of true. In other words, what I want to do is get rid of my millimeters. So I'm going to say I want to get rid of millimeters. I want to have meters. So let's see if we can do this. What's our known value ratio of meter to millimeters? Well, 1 meter is 1,000 millimeters. Okay, so if I do this, I'm going to cancel out those millimeters, and I'm going to get, so if I actually do the math now, I'm going to get, what do I get? Well, 70000. Let's just remove some of my picture here. We don't need this side, so I can get rid of this. Let's get rid of this. We don't need that. Let's carry on. So 700 There we go. And now I'm in, oops, what am I doing? Slits per meter. What I actually want is the meters per slit. So hopefully you can see, really what I want to do is I want the reciprocal of this. So this to the -1 is going to give me my, well, if I put that into my calculator, I'm going to get 1.428 something something, keep those in my calculator, times 10 to the 6. And if I flip these units around, it's actually meters per slit, and that's what I want. This is my D value. My D value is meters per slit. In other words, what's the distance between the slits? That's what I really need. Once I've got this, I should be able to fairly easily solve using my equations over here. Let's just go ahead and put some other values on. So I've got my wavelength, put that here. I've got my D value here. I just need this, this 26, which I'm going to use green for. This is the distance between the central maxima and the first bright line. So I'm going to put this in here. I'm going to put it in meters because that's going to make my life easier. So this distance here is 26 centimeters. What I'm trying to find is, I'm trying to find L, which is this distance here. And so hopefully you can see I need L, which is here. I've got wavelength, I've got D, I've got X, and my N number is just 1. Because if I went ahead and labeled these, this is my central maxima, this is N1, this is my N2, and so on. So I've got my N number is just 1, so I can kind of ignore that. So let's go ahead and solve now for L. So L is going to be equal to dx over lambda. And I'm just ignoring the N because I know that it's 1. And that's going to give me a value. Plug that into my calculator. 0.67532 meters. Checking my significant digits. It's 2, so I need this to be in 2 significant digits. In other words, 68 centimeters. But wait, there's more. I got to make sure that I'm checking my small angle approximation, because remember, this formula is derived using small angle approximation. So I got to double check, is the small angle approximation, is that true? So let's just quickly check. I've got my length, which I think I just calculated, and I've got my X value here. So let's do a quick, what are we going to do? We're going to go tan of the angle, hopefully it's less than 10, is the opposite over the adjacent. And that means it's going to be 26 over, let's just put 68, and then inverse tan. So my angle, if I was to plug that in, ends up being 20 degrees. Uh-oh, sad face, because that means I can't use my small angle approximation, which means this formula, which was derived from small angle approximation, is not valid. So I've fallen for the trick. Uh-oh, if I put this as my answer, I would be getting it wrong. What I need to do, hopefully you can see, I need to find the angle, because I know D. I can find the angle, and then I can actually find it using using trigonometry. So let's quickly do that. I'm going to say that the angle is, it's going to be the wavelength divided by D inverse sine. Okay, so my angle using this strategy is 22.6 degrees. Okay, so I know this angle. I'm going to put this in, 22.6 degrees, which means I can now just use tan of 26 is going to be equal to, well, the opposite, which is 26, over the length. And that means that my length is going to be 62.297. And if I keep that to 2 significant digits, then it's going to be 62 centimeters. Wow, what a difference. Check that out. 62 compared to 68. Hopefully you see why one is right and one is wrong. Small angle approximation is a big deal. We need to always remember it, always check it. You'll see this on diplomas. They will play with this idea. Make sure you're always checking. I always, when I'm doing my notes, I'll always put small angle approximation tick or cross just to see whether it's valid or not. Anyway, that's it for Unit 7. That's it for Unit 4. Next up will be Unit 5, which is atomic theory. See you next time.